Alright, here is one more project made by me, by Luiza, tiling at minimum cost with cooperation of Bob the Builder. Scenario 1. The firm. A construction firm employs two levels of tile installers. Craftsman and apprentice. Let's label craftsman X and apprentice Y. Craftsmen install 500 square feet of specialty tile, 100 square feet of plain tile, and 100 linear feet of trim in one day. An apprentice installs 100 square feet of specialty tile, 200 square feet of plain tile, and 100 linear feet of trim in one day. Scenario 3. What do they want? The firm has a one-day job that requires 2,000 feet of specialty tile, 1,600 square feet of plain tile, and 1,200 linear feet of trim. Scenario 4. The division of work. So here at the top are what the firm wants. And let's divide the work into what craftsman and apprentice can do. With this information, we can form our equations. For special tiles, trim tiles, and plain tiles. Now, the system of equations. 500x plus 100y equals 2000 of special tiles. 100x plus 100y equals 1200 of trim tile. 100x plus 200y equals 1600 of plain tile. Let's construct our objective function with the information given. The construction firm pays craftsmen $200 per day and pays apprentices $120 per day. Here are the values that we're going to need to construct our objective function. Let's label it. So, what each one receives per day and who receives this value. X and Y being craftsmen and apprentices. Let's join both together. 200x plus 120y. This is our objective function. Here is our system of inequalities, being the inequalities representing the first one special tiles, the second one trim tiles, and the plain tiles at least. And since it is a real-life example, x is greater than 0 and y is greater than 0. But why? Because you can't have negative labor costs. Let's graph. Let's graph the special tiles. So 500x plus 100y greater than or equal to 2000. Graphing the trim tile. 100x plus 100y greater than or equal to 1200. Graphing plain tiles. 100x plus 200y greater than or equal to 1600 tiles. And graphing the real-life constraints, which restrict the graph greater than or equal to 0 in x and greater than or equal to 0 in y. Let's join together all the graphs that we graphed. And we get the feasible region. First we get the vertices. 0, 20, 2, 10, 8, 4, and 16, 0, which forms our vertices for our feasible region. This is an unbounded feasible region, and any value inside this region will satisfy the wills of the firm to be completed. Now we will apply the vertices that we got to our objective function. Let's create a table. So we have the vertices, the objective function, and the result. So let's apply 0, 20. We apply 0 for x and 20 for y. And we got 2,400. 2, 10. We apply 2 for x and 10 for y. With that, we get 1,600. Then 8, 4. We apply 8 for x in our objective function and 4 for y. And we get 2,080. 16, 0. We apply 16 for x and 0 for y. And you get 3,200. Let's find the minimum cost. Answering: how many craftsmen and how many apprentices should be assigned to this job so that it can be completed in one day with the minimum labor cost? What is this minimum labor cost? In order to construct 2,000 square feet of specialty tile, 1,600 square feet of plain tile, and 1,200 linear feet of trim, paying $200 for craftsmen and $120 for apprentices a day, the firm should have 2 craftsmen and 10 apprentices to have the minimum labor cost of 1,600. Let's say that the apprentice wages increases from $120 to $150. With this new information, what will be the minimum labor cost? So what do we need to do? We need to change the objective function, the price of the day for the apprentices. So here is our first objective function. So we need to change the 120 to 150. And the other is the same thing. So this is our new objective function. So let's apply it to the points again. Let's create a table. X and Y, objective function and results. So we apply the same vertices in a different objective function and we get different results. With this different information, the minimum labor cost will be 1,900. In this case, how many craftsmen and how many apprentices should be assigned to this job so that it can be completed in one day with the minimum labor cost? What is the minimum labor cost? In order to construct 2,000 square feet of specialty tile, 1,600 square feet of plain tile, and 1,200 linear feet of trim, paying $200 for craftsmen, $150 for apprentices a day, the firm should have 2 craftsmen and 10 apprentices to have the minimum labor cost of $1,900. Answering 2. Do any points in a feasible region call for apprentices but no craftsmen? If so, is this a realistic scenario for the construction firm? Yes. Point 0, 20 employs 20 apprentices and no craftsmen. Mathematically, it is realistic, but when it comes to the functionality of the firm, in this scenario, it doesn't work. This happens because the apprentices are just learning until now. But if there are no craftsmen Who are they going to learn from? If there is not someone, a boss, to control the people learning, they will be without instructions, and when the build gets ready, it will fall soon. Answering 3, Part 1. What constraint could you add to ensure that every job has at least one craftsman assigned to do it? The constraint that I will add to my system to ensure that for each one apprentice there will be at least one craftsman is x greater than or equal to y. This means that for each apprentice there will be at least one craftsman or more. Here is the graph. And the feasible region. Inside this area, there is one craftsman for each apprentice, and a combination of craftsman and apprentice that will give the firm 2,000 square feet of specialty tile, 1,600 square feet of plain tile, and 1,200 linear feet of trim, paying $200 for a craftsman and $120 for apprentice a day. Answering 3, Part 2. What constraint could you add to ensure that every job has at least one craftsman assigned to do it? The constraint that I could add to my system to ensure that for every X numbers of apprentices, there will be at least one craftsman is X is greater than 1. X is greater than or equal to 1. This means that there will always be one craftsman at least, but not only one craftsman for one apprentice, as the one mentioned before. And here is the new graph. Inside this area there is at least one craftsman for how many apprentices there are. A combination of craftsmen and apprentices that will give the firm 2,000 square feet of specialty tile, 1,600 square feet of plain tile, and 1,200 linear feet of trim, paying $200 for craftsmen and $120 apprentices for a day. The union regulations constraint. Suppose that the union regulations require at least one craftsman for every 3 apprentices on a job. So the equation that I created was 3x equals to y. Then the inequality, 3x greater than or equal to y. But why this equation? It simply doesn't make sense when you look at it. So let's make sense of it in a graph. So what do you need to represent? You need to put 1x craftsman for each 3y apprentices. So let's make that. One craftsman for each 3 apprentices, one craftsman for each 3 apprentices, one craftsman for each 3 apprentices, and then you have your line. It makes completely sense. Now graphing with the new inequality. The vertices 3,9, 8,4, and 16,0. Inside this area there is one craftsman for each 3 apprentices, and a combination of craftsmen and apprentices that will give the firm the amount or more of tiles constructed than what the firm needs. A combination of craftsmen and apprentices that will give the firm 2,000 square feet of specialty tile, 1,600 square feet of plain tile, and 1,200 linear feet of trim, paying $200 for craftsmen and $120 for apprentices a day. Answering. Which of the vertices of the original feasible region from activity 2 satisfy the new constraint? The vertices of the original feasible region that satisfy the new constraints are 8,4 and 16,0. Let's take a look at these graphs. Graph comparison. 8,4 and 16,0 on both of the graphs. Let's take the first objective function, but with the new vertices. Let's make a table. X, y, objective function, and results. Let's apply 3,9. 200 times 3 plus 120 times 9 equals 1,680. 8,4. 200 times 8 plus 120 times 4 equals 2,080. 16,0. 200 times 16 plus 120 times 0 equals 3,200. What is the minimum now? The minimum. Using the new constraints and the original labor cost of $120 per day for apprentice, how many craftsmen and how many apprentices should be assigned to this job so that it can be completed in one day with the minimum labor cost? What is the minimum labor cost? In order to minimize the cost of the firm per day and have at least one craftsman for each 3 apprentices, should be employed 3 craftsmen and 9 apprentices. The minimum labor cost to the firm can make with this new constraint is 1,680.